Exact differential equation. What is an exact differential equation? A differential equation of the form m dx plus n dy is equal to 0, where m and n are some functions of x and y, is called an exact differential equation if del m upon del y is equal to del n upon del x. A differential equation of the form m dx plus n dy is equal to 0, where m and n are some functions of x and y, is called an exact differential equation if partial derivative of m with respect to y is exactly equal to partial derivative of n with respect to x. How to solve? Step 1. Let m dx plus n dy is equal to 0 is the equation to be solved. So first we have to check the partial derivative of m with respect to y and partial derivative of n with respect to x, and if these two are equal to each other, then we come to know the given differential equation is an exact differential equation. So step 2. The solution of an exact differential equation is given by integral m dx. We have to consider y as constant, while integrating m with respect to x, we have to consider y as constant, plus integral terms of n not containing x dy is equal to c. Now let us take an example. We have to solve 5x to the power 4 plus 3x square y square minus 2xy cube dx bracket 2x cube y minus 3x square y square minus 5y raised to the power 4 dy is equal to 0. So this is in the form m dx plus n dy is equal to 0, where m and n are functions of x and y. Comparing with this equation, we get m is equal to 5 x to the power 4 plus 3x square y square minus 2xy cube, and n is equal to 2x cube y minus 3x square y square minus 5y raised to the power 4. So let it be equation 1 and let it be equation number 2. Now differentiating equation 1 partially with respect to y and equation 2 partially with respect to x, we get, so if we differentiate equation number 1 partially with respect to y, on the left hand side we get del m over del y is equal to, in first term there is no y, so the whole term is considered to be constant because we are differentiating with respect to y partially, so terms of x are considered to be constant, so derivative is 0. In the next term, x square is considered to be constant and y differential of y square is 2y, so it becomes plus 6x square y. In the next term y cube is there, so differential of y cube will be 3y square, and 2x is considered to be constant, so minus 3 to the 6x y square. So we get 6x square y minus 6x y square. Now if we differentiate equation number 2 partially with respect to x, now the y is considered to be constant, so del n over del x is equal to, in the first term if we differentiate x cube, we get 3x square, 3 to the 6, 6x square y. In the next, if we differentiate with respect to x partially, so derivative of x square is 2x, so we get 2 3 the 6x y square, and the last term is 5y raised to power 4, which is considered to be constant when we differentiate it partially with respect to x, so its derivative is 0. So del m over del y is equal to 6x square y minus 6x y square, and del n over del x is also equal to 6x square y minus 6x y square. So it implies that del m over del y is equal to del n over del x. Now when we come to the conclusion that the given differential equation is an exact differential equation, because the necessary condition del m over del y is equal to del n over del x is satisfied, so the solution of the given exact differential equation will be integral, keeping y as constant, m dx plus integral terms of n not containing x dy is equal to c. So integral y as constant m, which is 5x to the power 4 plus 3x square y square minus 2xy cube dx plus integral terms of n not containing x. So if we observe in n, first term has x, so we have to ignore it. Second term has x, we have to ignore it. Third term doesn't have x, so we have to take only this term. So minus 5y raised to the power 4, minus 5y raised to the power 4 dy is equal to c. Now keeping y as constant, we have to integrate only x. We have to integrate only the terms of x. So in the first term 5 as it is, integral of x to the power 4 will be x to the power 5 upon 5 plus 3, integral of x square with respect to x will be x cube upon 3, and y square is taken as constant, minus 2, integral of x is x square upon 2, and y cube is taken as constant. Now next, plus into minus minus 5, integral of y raised to the power 4 with respect to y will be y raised to the power 5 upon 5 is equal to c. Simplifying, 5 is cancelled by 5, 3 is cancelled by 3, 2 is cancelled by 2, 5 is cancelled by 5. So we get x to the power 5 plus x cube y square minus x square y cube minus y raised to the power 5 is equal to c, which is the required solution of the given exact differential equation. Let us take second example, and that is solve y sec square x plus sec x tan x dx plus tan x plus 2y dy is equal to 0. So obviously this is the form m dx plus n dy is equal to 0. So comparing with this, we get m is equal to y sec square x plus sec x tan x, let it be equation number 1, and n is equal to tan x plus 2y, let it be equation number 2. Now differentiating equation 1 partially with respect to y, we get del m over del y partially with respect to y, that means differential of y is 1 and sec square x remains as it is, plus, and here the whole term has functions of x, there is no y, so whole term is considered to be constant when we differentiate it partially with respect to y, so differential of this term is 0. So finally we get sec square x, let it be equation number 3. Now differentiating equation 2 partially with respect to x, we get del n upon del x is equal to, first term is tan x whose differential is sec square x, and the next term is 2y, there is no x in the term, so this term is considered to be constant, so its differential is 0. Sec square x plus 0 is equal to sec square x, let it be equation number 4. So from equation 3 and 4, if we observe the right hand side, we come to the conclusion that del m over del y is equal to del n over del x, because both the right hand side have the same expression, sec square x, sec square x. So from equation 3 and 4, del m over del y is equal to del n over del x. So given differential equation is an exact differential equation because the necessary condition for is satisfied. The integral y as constant m dx plus integral terms of n not containing x dy is equal to c. So integral y as constant m. So we get m as y sec square x plus sec x tan x. So y sec square x plus sec x tan x dx plus integral terms of n not containing x. So we have to observe n, that is the coefficient of dy. As the first term has x, so we have to ignore it, and second term doesn't have x, so we have to take this term only. So 2y dy is equal to c. Now if we integrate this term with respect to x, keeping y as constant, so as we know well, integral of sec square x is tan x, so we get y tan x plus, and the second term is sec x tan x whose integral is sec x, so sec x plus 2, integral of y with respect to y is y square upon 2 is equal to c. Now here 2 is cancelled by 2, and finally we get y tan x plus sec x plus y square is equal to c, and that's it. This is the required solution of the given differential equation.